So we have discussed about simple harmonic motion, simple harmonic oscillator, anharmonic oscillator, damped harmonic oscillator, etc. in our last classes. So the oscillatory motions are over. Now we will discuss about wave motion. So what are wave motion? It's a familiar concept of nature and it's an important mode of transfer of energy. You know what are wave motions. You have already seen many examples in life like waves in sea and the waves formed when a stone is thrown into the pond. These are examples of wave motions that you have seen. And if we are shaking a string, the waves passing through the string, or a rope, these are examples of wave motion in our daily life. Okay, so what is wave motion? A wave motion can be considered as a disturbance which is caused by the particles of an elastic medium executing definite periodic vibrations about their mean position. So the oscillatory motions are also vibratory motions, which is vibrating about a mean position. It's a to and fro motion within a regular interval of time. Wave motion is a disturbance which is propagating through the medium like a vibration. Okay, while the vibration or the wave motion, the medium itself does not moving, but the energy is transferring from particles to particles. That is, the energy from one particle of the medium is transferring its energy to its nearest particles, and its energy is to its next nearest particles likewise, so that the disturbance is propagated as energy transfer in the medium. The medium does not travel itself, but the energy is transferring from particles to particles, and thus a disturbance produced at a point is propagating from point to a further distance. This is how a wave travels in a medium. This is known as wave motion. If the disturbance or state of motion is continuously transmitted along the same direction, then it is called a progressive wave. If it is along the same direction, then such waves are called progressive wave. In a wave motion, there is no bodily transfer of the medium through which the wave propagates. What travels towards in the medium is a state of motion which is passed on from one particle to the next particle on the wave as the wave advances. That's what I said earlier. That is, only the energy is transferring from one point to another point in the medium. No transfer of the whole medium as a wave. It's the energy transfer. So the wave motion is a mode of energy transfer. Okay, since during the propagation of the wave, particles of the medium lying on its path are thrown into vibrations in succession. Obviously, the waves pass on energy from one particle to next along their line of travel. That's what I said now. Hence, in a progressive wave motion, there is always a transmission of energy along the direction of propagation of the wave. So there is a transfer of energy along the direction of propagation of the wave. In stationary waves, the energy does not transfer from one place to another. That is, the stationary waves means suppose you have a rope with you, and it's two and is fixed. Two end is fixed. That is, one end is tied to one point, and the other end is tied to another point. And if you are making a disturbance in that rope, a wave motion will start executing in that rope, and it is a stationary motion. Means the wave motion starting from one end will end at the another point, and the disturbance may travel back. So it's a stationary mode of wave motion. So there is no energy transfer from one place to another in stationary wave motions. Okay, now there are two types of wave motion. These are transverse wave motion and longitude wave motion. Transverse and longitudinal. You know what is kind of motions? Transverse motions are wave motion in which the particles of the medium executes oscillatory motion about its mean position in a direction perpendicular to the direction of wave propagation. That is, if the wave is traveling in this direction, the particles vibrate in this direction, in the direction of in a direction perpendicular to the direction of propagation. That is, the wave will be like this. That is, the particle vibrate like this. That is perpendicular to this is the direction of propagation. The particles vibrate perpendicular to the direction of propagation. That kind of waves are known as transverse waves. The examples are ripples in the surface of water. This is one example. And light wave is an electromagnetic wave, and it is a transverse wave. And waves produced by transverse vibrations of the string. Transverse vibration. We are specifying the term transverse vibration because in a wave, in a string, we can produce parallel vibrations also, means vibrations parallel to the propagation of the wave. That's why here we are specifying here transverse vibration. Okay, so this kind of motion, in wave motion in which the particle vibrates perpendicular to the direction of propagation, is known as transverse. Examples are these. And what are longitudinal waves? Longitudinal waves are waves in which each particle of the medium executes oscillatory motion about its mean position along the direction of propagation. That is, if the direction of propagation is like this, the vibration is also will be like this. Means the particle vibrate from a mean position to this position, and will coming back and will move from and to and fro like this. That is, the motion will be in the direction of propagation itself. So that kind of motions are longitudinal waves. For example, if you are fixing a spring at one end and fixing a spring at one end, if we are pulling the spring from one side, this will execute this kind of motion, this kind of vibration. So it's a kind of longitudinal waves produced in this string. Examples of longitudinal waves are sound waves produced in air. Sound waves are examples of longitudinal waves, while light waves are examples of transverse waves. This is one example. And waves transmitted along a stretched spring. That's what I explained here. By compressing to one end this and releasing it. That's what I said now. These are two examples of longitudinal waves. Okay, so these are two types of wave motion, transverse and longitudinal waves. Now we will discuss about the general equation of wave motion. What is the general equation of wave motion? So when we are talking about this, suppose a wave train move along the direction of x-axis with velocity v. I have shown it here. This is y and this is x direction. Suppose the wave is traveling along this. The direction of propagation is along x direction with velocity v. Velocity of wave is v. Okay, v. If we assume the source of wave or any point of x-axis as the origin x is equal to 0, that is, suppose the origin of the wave is the point O, that is the source of the wave is that is, if we are throwing a stone to the pond, the point where the stone is thrown is the point, the source of the source or the origin of the wave produced in the water surface. That's what we are mean by the source or origin of the wave. So here O is the, we are imagining O is the source or origin of this wave propagating along this x direction with velocity v. If we assume if we assume the source of wave or any point of x-axis on the origin, x is equal to 0, then at any instant at any instant t, the displacement of the particle situated at the origin can be represented by the relation y is equal to f of t. So the displacement of the particle of the wave can be represented as f of t. This is at any time at any time t, at any time t. Okay, where f of t is the function of time. It will be a function of a time. It's quite obvious. So this will reach the point P at a distance x from O after x by v second. X by v second means velocity is, if x is the distance traveled from the source, then velocity can be represented as x by t. So in a time interval t, the wave is traveling at a speed v, a distance of x from the origin. So the velocity can be represented as x by t, so that the time can be represented as the time taken by the wave to travel from the source to the point P can be represented as t is equal to x by v. Okay, t is equal to x by v. So the waves started from the point O will reach the point, any point P at a time t is x, and a distance x from the origin. It is traveling with the speed v, so the time taken for this travel is x by v seconds. Hence at any instant t, the displacement y of the particle at P must be the same as the displacement at the origin x by v seconds earlier when produced at the source origin. That is, I can explain it like this. A wave is started from here, okay, at a time, and its displacement we have expressed as at any time as y is equal to f of t. And after x by v seconds, the wave this particle has the wave has reached here, so that its displacement can be represented as the displacement, the same displacement which produced at the point O at x by v times earlier. Okay, അതായത് ഇപ്പം നമ്മൾ ഒറിജിനിൽ നിന്നൊരു വേവ് പ്രൊഡ്യൂസ് ചെയ്തു, ഒറിജിനിൽ നിന്നൊരു വേവ് ഇതാണ് അതിൻ്റെ സോഴ്സ്. ഇതിൽ നിന്ന് അപ്പോൾ ഇതിൻ്റെ ഡിസ്പ്ലേസ്മെൻ്റ് അറ്റ് എനി ടൈം നമ്മൾ എഫ് ഓഫ് ടി എന്ന് പറഞ്ഞിട്ട് നമ്മൾ റെപ്രസെൻ്റ് ചെയ്തു. അപ്പോൾ എക്സ് ഡിസ്റ്റൻസ് ട്രാവൽ ചെയ്ത് കഴിയുമ്പോൾ ഈ വേവ് ഇതിൻ്റെ ഡിസ്റ്റർബൻസ്, ഇതിൻ്റെ ഡിസ്പ്ലേസ്മെൻറ്റ് നമുക്ക് എങ്ങനെ റെപ്രസെൻ്റ് ചെയ്യാം? ഇതാണപ്പോൾ എക്സ് ഡിസ്റ്റൻസ് ട്രാവൽ ചെയ്ത് കഴിഞ്ഞപ്പോൾ വേവിൻ്റെ ഡിസ്പ്ലേസ്മെൻറ്റ് പൊസിഷൻ ഈ പൊസിഷനിൽ നമ്മൾ കാണുകയാണെന്ന് വിചാരിക്കാം. അപ്പോൾ ആ സമയത്ത് ഇതിൻ്റെ വെലോസിറ്റി ടൈം ടേക്കൺ ഫോർ ദിസ് ട്രാവൽ ഇസ് എക്സ് ബൈ വി ആണ്. അപ്പോൾ ഇവിടെ പ്രൊഡ്യൂസ് ചെയ്യുന്ന ഡിസ്പ്ലേസ്മെൻ്റ് എന്ന് പറയുന്നത് ആക്ച്വലി എക്സ് ബൈ വി ടൈം മുൻപ് ഇവിടെ പ്രൊഡ്യൂസ് ചെയ്ത അതേ ഡിസ്പ്ലേസ്മെൻറ്റ് തന്നെയാണ്, അതേ ഡിസ്റ്റർബൻസ് തന്നെയാണ്. ഓക്കെ, അപ്പോൾ അതിൻ്റെ ഡിസ്പ്ലേസ്മെൻറ്റ് നമുക്ക് എങ്ങനെ റെപ്രസെൻ്റ് ചെയ്യാം? y is equal to എഫ് ഓഫ് ടി മൈനസ് എക്സ് ബൈ വി. ഓക്കെ, അതായത് ഒറിജിനൽ പ്രൊഡ്യൂസ് ചെയ്ത അതേ ഡിസ്പ്ലേസ്മെൻറ്റ് തന്നെയാണ്, അത് തന്നെയാണ് പിയിലെത്തിയത്. പക്ഷേ പിയിലെത്തുമ്പോൾ എന്താണ്, അത് എക്സ് ബൈ വി ടൈം മുൻപ് ഒറിജിനൽ പ്രൊഡ്യൂസ് ചെയ്ത ഡിസ്പ്ലേസ്മെൻ്റ് ആണ്. അതുകൊണ്ടാണ് ടി മൈനസ് എക്സ് ബൈ വി എന്ന് എഴുതുന്നത്. സോ ദിസ് ഈസ് ദ ഇക്വേഷൻ ഫോർ വേവ് ട്രാവലിംഗ് അലോങ് ദ പോസിറ്റീവ് എക്സ് ഡയറക്ഷൻ with constant velocity v. The function f determines the shape and size of the wave. So this is a function, the displacement is a function of time and velocity. Okay, അപ്പോൾ ഈ ഫങ്ഷൻ്റെ ക്യാരക്ടറിസ്റ്റിക്സ് അനുസരിച്ചിട്ട് ഇതിൻ്റെ ഷേപ്പ് വ്യത്യാസം ഉണ്ടായിരിക്കും. ദിസ് ക്യാൻ ബി എനി ഫങ്ഷൻ. ദിസ് ഇസ് എ ജനറൽ റെപ്രസെൻറ്റേഷൻ. ദിസ് എ ഫങ്ഷൻ ഓഫ് ടൈം ആൻഡ് വെലോസിറ്റി. So similarly, the equation of a wave moving along negative x direction can be represented as f of t plus x by v. So ഇപ്പോൾ നമ്മൾ പോസിറ്റീവ് ഡയറക്ഷനിൽ മൂവ് ചെയ്യുമ്പോൾ ഇവിടുത്തെ ഡിസ്റ്റർബൻസ് നമ്മളെങ്ങനെയാണ്, ഇവിടെ പ്രൊഡ്യൂസ് ചെയ്ത അതേ ഡിസ്റ്റർബൻസ് തന്നെയാണ് ഇവിടെ എത്തുന്നത്. പക്ഷേ അത് ഇവിടെ എത്തുമ്പോൾ അത് ഇവിടെ പ്രൊഡ്യൂസ് ചെയ്തതിൻ്റെ എക്സ് മൈനസ് വി കഴിഞ്ഞിട്ടാണ് ഇവിടെ എത്തുന്നത്. അതുകൊണ്ടാണ് ടി മൈനസ് എക്സ് ബൈ വി എന്ന് എഴുതുന്നത്. ഇനി ഇത് നെഗറ്റീവ് ഡയറക്ഷനിലായിരുന്നെങ്കിൽ, ഈ ഡയറക്ഷനിലായിരുന്നെങ്കിൽ എന്താണ്, ഇത് മൈനസ് ഡയറക്ഷനിലാണ്. അപ്പോൾ ആ മൈനസ് സൈനും കൂടി ആകുമ്പോൾ ഇതെന്ത് വരും, പ്ലസ് എക്സ് ബൈ വി. സോ നെഗറ്റീവ് എക്സ് ഡയറക്ഷനിൽ ദിസ് ഫംഗ്ഷൻ വിൽ ബി എഫ് ഓഫ് ടി പ്ലസ് എക്സ് ബൈ വി. ദിസ് ജനറൽ ഇക്വേഷൻ ഓഫ് വേവ് മൂവിങ് അലോങ് ദ എക്സ് ആക്സിസ് മേ ബി റെപ്രസെൻറ്റഡ് ആസ് y is equal to f of t minus x by v plus g of t plus x by v. So this is the general equations of wave. F and g are any two functions. This can be any two functions which depends on time and velocity. So if we are differentiating equation 1, this is a general general representation of wave traveling along the positive x direction. If we are differentiating this equation with respect to t and with respect to x separately, that is partial differentiation. So partial differentiation means if we have a function of two variable, if y is equal to f of xy. So partial differentiation means we are differentiating this function with respect to x. This is a function of two variable x and y. So we can differentiate this function with respect to x and with respect to y separately. So dou y by dou x, sorry, this is t, suppose this is t. So dou y by dou x is one differentiation and dou y by dou t is another differentiation. This is known as partial differentiation. That is difference if a function depends on more than one variable. This can be of three variable like z, etc. More than one variable, we means more than one variables, we can differentiate this function with respect to each variable separately. So each differentiation is known as partial differentiation. So here I was saying that this is a function of t and v. It's not like that. This is a function of t and time and position, t and x, because v is constant. Okay, so differentiating with respect to time, we will get f prime t minus x by v, and differentiating with respect to x, we will get f prime of t minus x by v and the differential of this term, that is minus 1 by v. Okay, here the differential of t is 1, that's why any coefficient is not appearing here. And if differentiating again, d square y by dt square is equal to f double prime t minus x by v, and dou square y by dou x square is equal to 1 by v square f double prime t minus x by v. Here one more 1 minus v will be appearing here, so that it will be 1 by v square, where f prime and f double prime are first and second derivatives of f. Now from equation 4 we can write dou y by dou x. Dou y by dou x is this. So this term, we can represent this term as dou y by dou x. This is nothing but dou y by dou t. So we can write this term as dou y by dou t. So this will become dou y by dou x is equal to minus 1 by v dou y by dou t. So that dou y by dou t, rearranging the terms, taking the v to the left side. So dou y by dou t is equal to minus v into dou y by dou x. So dou y by dou t is, y is the displacement and it is the time derivative of displacement. So it represents the particle velocity at the time t and instant x from the origin. And dou y by dou x, dou y by dou x is the slope of the yx curve, yx curve at the same instant and at that same point. Hence for waves traveling along the positive direction of x-axis, the particle velocity, this is the particle velocity, can be represented as minus of wave velocity, this is the wave velocity, minus wave velocity into slope of yx curve. Okay, where y is the displacement and x is the position where we are looking for the displacement of the particle in the wave. Now from equation 5, this is equation number 5, this is equation number 5, we can make the same substitution as that we have done in this equation. That's dou square y by dou x square is equal to 1 by v square into f double prime of t minus x by. So substituting for t minus x by v, dou square y by dou t square, because this term is dou square y by dou t square. So we will get dou square y by dou x square is equal to 1 by v square dou square y by dou t square, or dou square y by dou t square is equal to v square into dou square y by dou x square. This is the one-dimensional differential equation of wave motion. So this is very important and this is very famous equation. This is a general equation of wave motion. This should be remembered forever. This is a general equation and this is very famous equation of wave motion. This is one-dimensional. The common feature of all waves is the transmission of some sort of disturbance with the velocity characteristics of the medium. This disturbance is represented by a general symbol psi and the function, and this function function of t plus or minus x by v. So psi is equal to psi of t plus or minus x by v is the solution. That means the displacement can be represented. Here we have taken the wave is propagating along x direction. So in the y direction is the y direction represents displacement direction. So we have taken this equation as dou y by dou t or dou square y by dou t square form. This can be a general representation if we are putting psi instead of phi. So psi is equal to psi of t plus x by v is the solution of the wave equation, where we have replaced y by psi. Dou square psi by dou x square is equal to 1 by v square dou square psi by dou t square. It's a general representation. Both are same. If it is in 3 dimension, here this term will become dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. This is the 3-dimensional representation of wave equation, and this is known as Laplace. Laplace, that is dou square by dou x square plus dou square by dou y square plus dou square by dou z square is known as del square. Laplacian operator, it can be, so if this means this equation represents this operator operating on the side, del square psi. That is, this is a Laplacian operator operating on the wave function psi. That is this equation. So we can write this equation as del square psi is equal to 1 by v square into dou square psi by dou t square. This is the wave equation in 3-dimensional. Okay, here psi is the wave function of the wave, and if the wave function is determined for a particular situation we can know the form of the wave and its wavelength. So if we know the wave function, we can we know form of wave function, we can determine the wavelength. Okay, so this is all about the equation of general equation of wave motion. So this is the general equation of wave motion. This is one-dimensional differential equation and this is three-dimensional differential equation, and the displacement of this particle of wave can be represented in the like this. If the direction of propagation is in positive direction, this will be in the form. If it is in the negative direction, this will be in the form, and the general representation is like this. Okay.